So good afternoon to all of you from different universities and institutes who are attending this lecture on space-enabled products and services for disaster management, Indian perspective. And we will be discussing some fundamental aspects of disaster management using space science and why space science is critical today. And some of the examples we will give from the Indian scenario and also some foreign examples. And at the end, we'll discuss about the challenges and the future ahead. So I hope all of you are ready and we can start now. Now, the first slide, I would like to re-emphasize this point that why space science, remote sensing or space technology is crucial today. That is essentially due to some recent developments. So the most important point is the ever increasing pixel resolution. So now you must be aware that we can get now 30 centimeter resolution data sets from at a very affordable cost from various vendors, including the government agencies and private agencies. Mostly the private players are very active at providing very high resolution data, which is now 30 centimeter resolution data is now they have made it possible. And this is a very crucial development that very high resolution data sets are coming into, these are now being made available. Now at this point, I like to also mention that high resolution means the image interpretation skill sets, what is required is less. So the reverse is that, for the low resolution, the skill set is high skill set is required to identify a feature. Sometimes it's difficult even to identify a feature. So high resolution data, what is being made available today, that is very straightforward, like seeing an image or seeing a picture and identify certain objects. So that's the reason that why these high resolution data sets are very popular. But at the same time, since most of you are from the academic background, I would like to re-emphasize one point that even the medium resolution or not so high resolution, what we have seen, like the 5.8 meter resolution data sets or 2.5 meter resolution, our Cartosat 1 data set and 5.8 meter resolution LIS4 data sets are also equally good. Only what is required is some kind of a higher skill set is required to interpret those data, and whereas this kind of less than a meter resolution data sets are definitely straightforward, this data can be used with even lesser amount of skill to interpret the data. And now we have the agile satellite systems and the low orbit constellation, and the availability of data anytime, anywhere from this satellite platform has become a reality. And we may not be, at this moment, we may not be able to get it, but it is possible. Certainly the technology exists today to acquire the data anytime, anywhere. If we combine the capability of the space-enabled government sector and the private sector, if we combine together, which is a difficult task, I agree that some of you may feel that, in the time of crisis, it may not be always possible, but that is the present scenario. I hope the scenario is likely to change with the coordinated effort of private players and government agencies in the event of disaster management. Particularly, they should come together. But what I am emphasizing is the technology exists today that anytime, anywhere satellite imaging is a reality. Then we have the optical, microwave, thermal, hyperspectral imaging, complete coverage of this, the complex technologies, and in a very seamless manner, it's possible to acquire data from different regions of the electromagnetic range, and that also helps a lot. That some of the material properties can be sensed using thermal sensors, and some can be acquired or some can be observed better using the microwave sensors, and so also optical sensors. So the information can be used in a complementary manner from different set of sensors. So that is the advantage, and that is also today possible. Then very interesting development has taken place. The aerial sensors on board of aircraft and drone, these have overcome some of the limitations of satellite-based observation. In the steep terrain like Himalaya and many other hilly terrain, due to the extreme topography, sometimes some features are not seen very nicely on the satellite images. Whereas this can be complemented, or this difficulty can be overcome by the aircraft and the UAV, unmanned aerial vehicles, or popularly what we call them drone, which can fly around and take images from different angles, and it can complement to the satellite-based observation. So this is the point number 5. What I re-emphasize again: the drone and the aerial sensors. These actually are playing a major role in the event of disaster. We have seen it during the Nepal earthquake 2015 and many other disaster monitoring rescue operation. We have observed the role played by the drone or the unmanned aerial vehicles in providing the critical information in a most cost-effective manner, timely manner, and which has eventually helped the relief operations and also rescue missions. Another important point is the ground-based observation based on the LiDAR or the radar. It can also provide a lot of information, but this deployment of LiDAR and radar is only limited in certain areas, critical areas, mostly abroad, and temporarily in India, certain locations, certain sensors have been placed to acquire the data, but even today, we don't have the continuous observation using these technologies of any, the disaster-prone areas. For example, particularly with respect to landslides. So this is one emerging area. It's a possibility, and which can be realized with a larger amount of investment because of this technology is at the moment is expensive. Then certain geophysical investigations, which essentially probes the earth, the areas below the earth or below the surface. So these can be integrated with the space-based observation. So the information what you get from the space-based observation can be integrated with the subsurface information what we get from the geophysical investigation. And sometimes the space gravity mission and magnetic mission also provides information from space, not only from ground, also from space about the geophysical properties of Earth, which can be integrated. So the new emerging approach is that imaging from space, from ground, and below the ground, and the whole thing is we have to provide integrated solution mainly for the geological investigations, but that essentially for the landslide and earthquake I have mentioned, but it can be used for other applications as well. So keeping pace with new technology, keeping pace with new technology is a challenge, and what is important here is the capacity building and the expertise, development of expertise to use the different satellite data products in a meaningful manner, and not only use, it has to be deployed beyond the academic arena. That is a real area, real disaster management. This has to be demonstrated and integrated. So that is the key challenge even remains today, and we will see the promises from some of the applications which follows now. To again draw your attention to different stages of the disaster management. Disaster management, as it is seen over here. So disaster strikes immediately followed by the response. So this is one area. A response is a stage that is normally from a couple of hours to a couple of days after the disaster, and the prime focus is on the relief rescue mission. And during that time, there are specific requirement of the satellite data. And at the same time, we know that the time we take to respond is basically time we lose. So the criticality is how quick we get the information and how quickly we derive information from satellite data. First is satellite data has to be acquired at the quickest possible time. So there the bandwidth and other communication issues come into play, and people have to work on that to reduce the time which is required to acquire the satellite data. Then deriving the meaningful information from satellite data, and then communicating this information to the relevant people. So a lot of data can be obtained from the existing database. Disaster extent maps, this can be prepared from the immediately acquired satellite data, and the population affected can be known. Information collection and communication, this is very, very critical here. Evacuation and shelter, this can be managed very well, and dispatching the resources for these missions also can be done, and early damage assessment. So this early damage assessment is the very quickest damage assessment, and you like to know within few hours what is the damage happened, and accordingly the relief rescue team can be dispatched. So all that this is a job of few hours to few days, and the requirement of the satellite data is quickest possible. And second thing is that it's not very detailed information what is required at this stage. At this stage, actually, you cannot afford to do modeling or lengthy data processing. As a predetermined manner, automated manner, certain key processings have to be carried out, and some kind of a very practical approach has to be followed. The bottom line is that at the quickest possible to provide the information which will reduce the death, the number of casualties, and will ensure the quick recovery. Then after the response comes the relief, which often goes together sometimes with the response. But relief is the one during which we provide the search and rescue operation, debris or the rubble removal, delivery of the relief. So this is couple of days. It can start immediately, but it may continue for a little longer, and it is not the immediate response, but it is the response which continues for a little longer than the quickest response response phase what you understand. Then comes the recovery and reconstruction rehabilitation, and that is the time when the special planning has to be done, infrastructure planning with respect to infrastructure, water, communication, schooling, agriculture and housing sector we have to see, because our aim is that as quick as possible we have to come back to a stage where we were there before the disaster struck. So that's the reason quick recovery, and for quick recovery some kind of a planning management is required, and that is where also remote sensing can play a role. So these are the three stages, which normally the words start with R. We have kept it R so that easier to remember: recovery, relief, and the response. And immediately it follows, these three stages follow the disaster, and the requirement are slightly different. More or less they are same during response and relief stage, and slightly different during the recovery stage. However, the bottom line is that the critical information has to come at the quickest possible time. So then we have, before the disaster, we have three more stages: prevention, prediction, and preparedness. So certain preventive measures can be, mitigation measures can be thought before the disaster strikes, and this can be planned, studies can be done. So that is where there is no time constraint. So we can do a lot of processing, data processing, modeling, mathematical modeling, all that can be done. So that involves hazard zonation, modeling, simulation, risk vulnerability assessment, structural, non-structural measures, what is to be taken up in the event of disaster. And then after doing that, we have to work on the prediction and early warning. So that is about the forecasting, monitoring, or the scenario identification, or we can create a scenario that certain earthquake, if that strikes, so which are the areas likely to be affected. Such exercises can be carried out. So we are getting into preparation stage. Then comes the actual preparedness stage, where the resource inventory has to be made, logistic planning, evacuation planning, communication planning has to be done. So prediction, early warning, and preparedness, that goes hand in hand after the prevention and mitigation stage. So these two stages are almost the last two stages before the disaster. They go hand in hand, and this ensures that certain steps, certain actions they have to be taken in a proactive manner such that the impact of the disaster is minimum. So this is the whole disaster management cycle, and this is very interesting to know that each disaster, the requirement is different in different stages. So there may be some similarity, but one has to see very carefully with respect to landslide, with respect to earthquake, or with respect to flood. So what we should be doing in the 6 stages of disaster management, and what are the information or what are the help we can expect from the space, the space agencies or the space technology. So this has to be well understood, well debated, well studied, and finally at the policy implementation level, this should be worked out that which type of information is required to be implemented during this with respect to disaster management. And to give you an example that how the space inputs have been used for the flood management. So I have just given the mitigation stage, what is to be provided, hazard zonation. In the warning phase, inundation simulation can be done and provide this information can be provided. During response phase, we can do the actual mapping of the flood inundation, and post-disaster phase, we can look at the flood control measures. So this is with respect to flood management, how in different stages of disaster management with respect to only flood, what can be done or what is in practice people have been doing. So this is just one example. Similarly for earthquake, landslide, forest fire, any disaster you name, we have to think what can be done. It's country in India, a lot of research agencies, National Remote Sensing Agency, Remote Sensing Center, Space Application Center, IARS, and there are many other institutes who are using space science for disaster management purpose. A lot of work is being done, but only thing is we have to see that what type of information is being provided in what phase, and how that information has to reach to the people in a shortest possible time, such that during the disaster or before the disaster people can utilize this information to ultimately minimize the impact of disaster. The whole idea is that the space technology what we talk today must work towards achieving some kind of a zero casualty. Can we achieve a zero casualty using various technology and management practices, best practices? This is what is a tall order claim, I would say, but this is what actually people have tried, and partially to a great extent they have been successful. We have seen in the Cyclone Odisha 2000, a couple of years back, it has been seen that how the actual death toll reduced to double-digit figure from 1999 when the death toll was more than 10,000. So more than 10,000 super cyclone in 1999, they came down to double-digit figure only during the Phylline cyclone. So that indicates that it is possible to reduce substantial the death and destruction. And another important thing is that not only reduction of the death and destruction, recovery. The recovery happened in case of Phylline cyclone within a day or two. So now we can always think about the recovery of after the disaster. 24 hours recovery or 48 hours recovery is a reality if we plan it very, very well. So disasters we cannot stop, but we can reduce their impact in this way, and space technology was used to a great extent along with the good management practice and the many proactive action which Odisha government took during the Phylline cyclone. So our aim is that providing these technological solutions with the ultimate aim of reaching a zero casualty status and 24 hours recovery. So this is a tall order claim, but at the same time we must strive towards that. Now looking at this Indian imaging capability, India, all of you know that India has done tremendously well in terms of space-based applications in the country. And not only in the country, also globally it is recognized that India is one of the strongest players in space technology application for developmental needs. And we have approximately 14 operational remote sensing satellites, and resolution wise we cover 1 kilometer to less than a meter, and 24 days coverage to 24/7 coverage. Very soon we will have a satellite image coming at 50-meter resolution 24/7, and we have optical to microwave capability, and we are continuously increasing our capability in terms of number of satellites, in terms of coverage, and in terms of spatial and the spectral resolution. So we are in a comfortable position, in a good position, I would say, that we have good amount of satellite data sets available from different sensors, and this is the Indian capability. This is complemented by the foreign capability or the capability of other countries and private players in the event of disaster. So question is that this whole set of data sets which have different application in different stages, these data sets along with the data which is available from different foreign satellites and agencies together can do a lot, but the main problem is that the capacity building. That's Indian Institute of Remote Sensing focuses. Capacity building is a key area, and this is certain type of skill sets are to be developed and with a practical application in mind. So it's not easy to do that. Mainly the disaster management, it has to be understood in the ground, on the ground, and which technology works, which doesn't work, we have to see. So it's a big challenge. It's not something you can do it sitting in a computer room or sitting in a satellite reception center. You cannot design certain things. So it has to be translated into say, product and services on the ground. So the linkage with the ground is very, very critical, and that is a reason that that's the reason as well as the challenge that why many cases we are even though we have the best of best technology, why even we have not reached up to the we have not utilized the potential to a great extent, to maximum extent, is mainly due to the capacity building needs which are not fulfilled and which are not taken very seriously actually. So that is the one reason that Indian Institute of Remote Sensing dedicates its efforts towards capacity building. That's one of the reasons that why we are delivering this lecture today. And during the disaster, very interesting to see that there are major space agencies. They have reached a agreement to share and the data sets, share the space assets during the disaster. So that includes disaster response, multi-satellite data acquisition, fast data turnaround, priority acquisition, and archive retrieval and spacecraft tasking, data processing at predetermined level. As I have said, you cannot design a new level of data processing. It has to be done in a pre-decided manner. Space agency contributing to image and data, and space agency, they have initiative for value-added data fusion also. So there are major space agencies, all of them are now member, and this service is now provided to many countries, many agencies within a country, and many countries directly. This is one example of the Kosi flood in 2008, and this is a major flood event in Bihar which happened, and international agencies, Indian agencies, they all provided very, very crucial information which helped in rescue and relief operation to reduce the impact of the disaster. This disaster affected almost 3.2 million people, and the death toll was less than 1,000. And to a great extent, space technology in front of you, which was used, this information, so these products were provided to the rescue and the relief. Starting from rescue, relief to rehabilitation, all these products were useful. And date-wise, you can see how the flood water was increasing. This also could be mapped, and exactly where the breaching happened, and how the Kosi River, which was flowing towards west, started flowing towards east. That's the reason actually, after 150 or 170 years, this is shifted its course, and that's the reason why there was massive inundation and destruction. So all this could be known from the different satellite data products. This is another example of the Odisha flood in 2011, and you can see the areas before the flooding and areas after the flooding. This is mainly due to the Mahanadi and other rivers, northern Odisha rivers, and so this provided again information on different flooding status. And also, by taking a temporal data set, one can know for how long the area was under flood water. Accordingly, the crop damage can be assessed. Some of the crop can withstand water up to 24 hours. Some crop they cannot withstand. So based on the how long the area was underwater, the damage can be assessed properly. We will now move on to earthquake hazard mitigation. So what are the things possible for the earthquake hazard mitigation are the following: active fault mapping, earthquake precursor monitoring, ground motion and liquefaction modeling, tsunami and storm surge modeling, earthquake triggered landslide modeling, then quick damage assessment. So this is something which can be used in the event of earthquake. IRS has recently set up various permanent GPS stations which are monitoring the earthquake. They are monitoring the crustal deformation and how the the Himalayan region is moving, at what rate it is moving, whether it is a 50 millimeter or 40 millimeter. So precisely we come to know the motion, and by using 24/7 observation. And these instruments also receive a signal from which we calculate the total electron content in the ionosphere, and this seems to be a change in the total electron content before an earthquake. So globally it has been observed, and many earthquakes it has been seen that the ionosphere responds to the certain phenomena before the earthquake happens. So these instruments are capable of receiving the information, which information can be modeled to derive the total electron content in the ionosphere. And this fluctuation in the ionosphere can be studied to get some early indication about the earthquake. It's a path-breaking study which IRS has done, and I'd like to show you a couple of results from this. And this is one example before the Nepal earthquake 2015. The earthquake happened on 25th of April, and before that we had seen some kind of perturbations, disturbances. Similarly, this earthquake on 25th was followed by another earthquake on 26th and also 12th of May. So before 12th of May, we had seen some kind of anomaly in the total electron content on 11th of May, and also for this 24th and 25th and 26th event, which is a major earthquake event, 25th and 26th April event, we had seen before 14 days some kind of perturbations, and also closer to that date also we had seen some perturbations. But important changes or the anomaly what we saw before 14 days were very, very crucial. And using those anomaly, we try to find out spatially where is the anomaly, and we see this anomaly is very, very close to the earthquake where it occurred. So in a global map, this anomaly has been seen, and this anomaly was at a particular time was only seen above the the epicenter region, and this information was available before, you can say, before 14 days. 11th of April we had seen this anomaly. This study was done after the earthquake, and so this information could not be utilized, but this is a study which we carried out recent time, and we are developing now a technique that how we can do this thing actually before an earthquake, so that although we may not know the exact time of the earthquake, but we can, to a great extent, we can know the the place where the earthquake likely to happen within a time frame of 10 to 15 days. So studies are going on, and using these studies we are moving ahead, and this is a very important information how the earthquake, early indication of earthquake we can get. So we are not calling it early warning. Reason is that in early warning you have to tell about the magnitude, about the place, about the time. Three things precisely you have to tell. So we are not in a position to tell these three things very precisely, but what we get information is the early indication of earthquake. So that's the reason we call it earthquake precursor, and earthquake precursor are very helpful to reduce the impact of the disaster. This is one example from the Haiti earthquake, and immediately after the earthquake such kind of maps were prepared showing the damage which has happened in the Haiti city. This city was in the Haiti, around 225,000 people had died. Entire the capital city was completely devastated, and this is Latin American country, and this is not a very rich country. It's one of the poor countries, and you can see the GIS layers have been overlaid, and satellite derived information has been overlaid, and that provides information about which areas must have been affected. Accordingly, relief rescue missions were provided in this region. Now I take your attention to 2005 Kashmir earthquake, which is 7.6 magnitude, and almost in India and POK region it killed over 80,000, around 75,000 people, and there was a huge landslide which occurred, and this landslide, because of the earthquake, actually killed almost 1,000 people here. And you can see that in the hilly area, when the earthquake occurs, it not only creates one, there were around 3,000 landslides, more than 3,000 landslides. So all could be mapped, and one of the biggest landslides we have tried to find out how much material has been displaced, how much material has been deposited, and whether it has blocked any river. You can see here the river was blocked, so some kind of a siphoning had to be made to release the water. The upper this figure indicates the red line. What you see is a causative fault of the earthquake. Some kind of advanced processing has been carried out, which indicates the fault. This area is very difficult to map this fault, but using the pre and the post satellite data, using a lot of digital image processing, so this fault could be detected, and this had to be correlated with the earlier known faults of the region to interpret their significance. This is now looking at the Bhuj earthquake 2001. Some of you may be remembering that this was a very devastating earthquake in India, and this earthquake killed almost 13,000 people, and areas were affected mostly in the Gujarat, and some places adjoining states were also affected, but mainly in the Gujarat. So liquefaction modeling we have attempted. So this is a process which the land behaves like liquid for a certain time, duration of the earthquake, and it's not the ground vibration which destroys or the causes destruction. It's basically the liquefaction means the ground behaves like liquid for 30 to 40 seconds. So that is what causes the tumbling of the buildings, collapse of the buildings. But however, this can be mapped. Not only mapped, this can be modeled actually. It's not a mapping, it's a modeled exercise, and it can be done, this kind of modeling can be done within 10 minutes. And based on the model output, we can know which areas must have been affected by liquefaction. Accordingly, the relief rescue measures can be sent to those localities. So we demonstrated very successfully how the modeling exercise can be done quickly. And this is similar exercise we have tried to do for the Nepal earthquake within 1 hour or so after the event. Because in the Bhuj case, we could do this exercise after a month or so. This was because that was the first time we were doing it. But in case of this Nepal earthquake, based on that experience, we could know immediately, and we could provide the information to the Bihar State Disaster Management Authority and NDMA that destruction must have happened in some of the places what model suggested, and we provide this information within 1 hour or so. And by the evening, actually, we saw the destruction report coming from the same places. So this shows that this technology works, and we can make models, we can make simulations as per the actual scenario. And I can inform you that this is not the precise information what we give, but this is based on certain assumptions, and this is the information what is provided at the golden hour. The golden hour means is within the few hours of the event. So that is what the information is provided. So we don't want to be precise at that point of time. So whatever information we get, we try to get the best solution, and which is very practical. So this is what was provided immediately. So subsequently we improved our model and simulation. Now we move on to the landslide, which is a very recurring phenomena in the Himalaya and many parts in the country. You'll be surprised to know that the Kerala flood, although it is known as the Kerala flood disaster, but maximum death destruction has happened because of the landslides in the Idukki and the surrounding regions. So landslides are the main culprit. Now it is emerging that out of 450 deaths, around 400 people have died due to the landslides caused by this flooding and the heavy rain. So landslides are very, very critical, And landslide monitoring is possible using medium and high resolution satellite data. Movement detection is also possible using interferometry SAR. We can do predictive modeling for landslides, and we can do also the early warning we can do. And seismicity induced landslide modeling is also possible, because Nepal earthquake, Kashmir earthquake, and many earthquakes in the hilly area, it has been seen that 30% of the death and destruction due to earthquake can be due to actually landslide induced by the earthquake. So one has to keep note of this fact that 30% destruction in the hilly area will be due to landslides caused by an earthquake. So earthquake destruction, it has been seen in many cases. So that's the reason we have to give a lot of importance to seismicity induced landslide modeling. So the pictures what you see is the white patch. So this is a landslide which can be easily mapped, but not always, but most of the cases you can easily see this as a white patch. And landslide hazard zonation map has been shown on this lower right corner, and the lower left corner you see interferometry SAR product showing those fringes which indicates the movement detected between 22nd June and 27th July 2004. So within a month, how the ground has moved due to landslide has been observed. And keep in mind that this is rainy season. So during rainy season, we don't get good quality optical data. That's the reason why this microwave data has been utilized to find out the movement due to landslides. Now these are the things, there are a lot of limitations were there in terms of data availability to carry out such studies. Now new missions, and there are some new missions have come up now which provide a lot more data sets to take up this study. And India and the NASA, they are going to have a new mission we know is known as the NISAR, which is primarily its aims at providing this kind of information at a higher temporal resolution or temporal coverage. It's very interesting that look at the landslide global map. You can see the Himalaya region has emerged as a hotspot. All the red dots what you see, 2008 event, 2007, 2006 event, most of the dots are actually closer to the Himalaya. So Himalaya has emerged as a hotspot of landslide. That's the reason, including some of the Western Ghat regions. So that's the reason why we should give greater importance to landslides. And this is very interesting. This landslide and the climate change are linked, and we see in the Himalayan region. So this region, starting from the west to east or east to west, we see the landslides that are linked to mass wasting and also to the climate change. So all are integrated. That's the reason why this has to be studied in a thoroughly to predict and to prevent and minimize the disaster. So one attempt has been made here. Apart from the landslide hazard zonation and landslide mapping, we have tried to find out the intensity and duration. What is the intensity rainfall and how long does it should rain to cause landslide. So this has been attempted, and we have got an equation. So based on which we can actually say that how long it will take if the intensity is known. For a certain known intensity, how long the rain has to be there to cause landslide. So such kind of models are possible using the existing data sets. And this is a hazard zonation in Uttarkasi region. All the red and pink areas are the high hazard areas, and that is where we have seen landslides have occurred subsequently. So this map was prepared before the landslide occurred in the Uttarkasi region, and in the Uttarkasi region we had showed some red patches. Exactly on the red patch, the landslide occurred after a couple of years. So this indicates that the vulnerable location or the critical locations can be identified in advance. And if there is a population at a risk in closer to those areas, we can do some kind of simulation. We can do a lot of exercise to evacuate people to safety, and take a proper guard against such natural disasters. And very interesting, some of the developmental activities like the dam construction, reservoir also leads to some kind of slope instability. And it may be temporary phenomena, but nevertheless it is very critical to study the areas which are closer to the reservoirs. A lot of dams are being constructed in the Himalayan region, and we have to monitor the dam rim area, so for possible changes due to the water level fluctuations. There could be landslides, there could be other types of mass wasting, including erosion, and this is what we try to study. And we saw satellite data reveals a lot of new landslides which were developed immediately after the inundation. So high resolution satellite data sets from the digital globe clearly shows some of the landslides. This white patch is not landslide. Basically, this is a the highest level and the lowest level water level. But the thin line, what you see, this very thin line, they are the ones indicate the landslide scar, or the landslide, you can say, the initiation point. And similarly, there are many satellite data like Cartosat-1 has been used. Then the digital globe QuickBar has been used, 2.4 meter multispectral. So all the data sets show that the reservoir rim of the Tehri Dam area, it developed certain kind of landslides, and we expect in future those to settle down, and initial part more such landslides or slope stability problems are expected, and this monitoring of this satellite data also reveals such failures, slope failures along the rim areas. But we expect it to stabilize in due course of time. And another example, the lake landslide happened in Nepal, and there was a threat of due to the landslide which blocked the river Sankosi, and there was a threat that in India, if the dam, the natural dam which has been created due to landslide, if that breaches, so there will be flooding again in the Kosi region. So the Kosi flood region I had shown you, 2008 people had experienced the bad flood of 2008, and they were all scared that in case these dam breaches and again there will be flood. So that's the reason that sometimes the disaster may happen in a neighboring country and may affect India. So that's the reason we have to study also the landslides or certain things which happen across the border, our national border, to safeguard our people. So the landslide could be mapped, and the amount of water which is available, this could be also known, and certain modeling also we did to see that if there is a real breach, how long time we will get to response. So these were also worked out. And this comes to the Kedarnath disaster 2013, and you can see those landslides, avalanches, all this material which has come on prior to the devastation which happened on 17th of June 2013. So this clearly tells that the entire region received a lot of rain, a lot of snow melting happened, and because of that, a lot of debris flow, debris sliding, or debris fall happened prior to the devastation on 17th actually. And then we also moved to the Chorabarita lake to see that lake which was breached resulted in killing of more than actually 5,000 people. And you can see this is before the disaster. Right hand side lower image shows before the disaster, and this left hand side bottom picture shows the after the disaster. So clearly shows the influence of landslides, the lake which has been emptied, and also the terrain before and terrain after. So this is very interesting. A lot of information about the length, breadth, and the height of the or depth of the lake could be obtained using the satellite data products. Our people also went to the field to check. We found there is a close similarity, or the figures are more or less same. And this is what our field people are working in the field, and to know about the depth of water, possible water, and all these things, because it's very important to know that during this disaster there is no eyewitness, there is no measurement. It is a remote locality, and it is all satellite data have to be used. Various indirect methods have to be used to find out how much water was there, what was the velocity water came and swept away 5,000 people at least. So that's satellite data provides a lot of information about the past data. The digital elevation model was generated, and that provided clue onto which was the responsible main which phenomena. It's a flash flood or the landslides were responsible for the disaster. So we see a clear-cut contribution of the landslide as has been revealed in the Kerala case. In Kerala case, actually, people have gone down the survey and they found out that landslides are very, they were the devastating, clear-cut. But here, a lot of debate is still there, although we have proved that the landslides are the critical, and landslides were the main contributing factor of the 2013 Kedarnath disaster. But still, people think that it's the water which came, which killed people. That of course, we agree. That's the end result or the end effect. But actually, the channels were choked previous day. That's the reason why water could not flow through their existing channels, and finally it had to flow through the town, sweeping away, people. And this is the digital elevation model actually, which revealed and proved that how the Mandakini and Saraswati were flowing at almost the same level, and that is only 3 to 4 meter lower than the place where the temple is located. 3 to 4 meter can be easily filled up by debris, and which was happened during the 15th and 16th. And 17th morning when the lake breached, there was no channel free. All the channels were covered by the debris, so channels were not free to get or receive those debris. As a result, on 17th morning, the water had to flow through the center of the Kedarnath, and many in the whole process, many people died. For the forest fire is one area which is partly attributed to a great extent attributed to the man-made disaster, but however, the space technology can help to know whenever there is a fire within a couple of hours, we can know, and remedial measures can be taken up to minimize the spread, minimize the impact of such forest fire. This is another example about how the glacier lakes are increasing their size, and finally they will become so big, and one day they will breach, which will affect our hydropower as well as it will cause flooding in the downstream region. So monitoring of lake formation is very, very critical in the Himalaya, and there are several thousands of lakes are there. They have to be studied, and bigger ones have to be monitored, and their destruction potential in terms of glacial lake outburst flood has to be assessed. So we are coming towards close, and disaster management, what are the key issues? Disaster monitoring system we have to develop. Early warning we have to pay a lot of attention. Quality response. So no government today can afford not to respond to a disaster anywhere. I mean, most of the developing and the developed countries, government has to respond. So what is the important thing is what is the quality of response. So I can give many examples where the quality of response could have been much better using the technological aid and inputs. So another thing is the build back better, that refers to rehabilitation, reconstruction after the disaster has to be much better, much improved, such that when we do the recovery, we are in a situation after the recovery in a much better situation than before we were. So this is conceptually known as the build back better. That is why remote sensing can be used. And the risk reduction, the reduction of the risk with better planning is a critical area again. That should be taken. That should be taken up. And there are some take-home points and key issues that use Earth observation for both personal safety and rescue mission. I would say I will appeal to all of you who are attending this course, this lecture. It's not only that what I'm telling is required only for some agencies or somebody else, but even if you are visiting some places and you are caught in disaster, satellite data sets you can access through your mobile, and through various means you can access, and this can help, this can improve, this can help to in your safety, personal safety. So even the rescue relief workers who are working, they can use this technology first to ensure their own safety, then to indulge in the rescue mission or get involved in the rescue mission. And it's very important to know how to interpret satellite data and use GIS, get some basic training and capacity building. It's very, very important, and it's not that easy that you can interpret the satellite data always. Always you will not get the high resolution data. You have to depend on moderate resolution data, and that is where the image interpretation skill has to be developed, and it's not easy. And it's easy in the sense that with some practice you can develop this skill, but is more practice is required to interpret the satellite data with a lot of experience. Satellite data, a lot of varieties one has to see. That is what the Indian Institute of Remote Sensing is known for. And globally, there are various data sets we have acquired since 1960s, mainly the aerial photographs, followed by the satellite images 70s onwards. And a lot of satellite data is there. People can see, interpret, go to field, cross-check. So the satellite remote sensing, while interpreting the data, one has to see the ground reality and link the ground reality onto the image interpretation. So this linking of ground reality and image interpretation, that requires certain amount of skill. Although the skill set required is less if you have very high resolution data. Then if you have the high resolution data, often the coverage of the data is less. The aerial coverage is less because it will cover only 4 to 5 square kilometer or even maybe less if you ask for a 30 centimeter data set. So there is always a trade-off. So that's the reason that why the moderate resolution or the not so high resolution, say 0.25, 2.5 meter resolution or 5 meter resolution data set, I would say that they are the most ideal for disaster monitoring purposes. And that requires certain amount of interpretation skill. So one has to invest in interpretation skill or the data processing. So that's the reason why capacity building is required. Basic GIS operation one should understand. That will also help overlaying different types of maps and see those villages critical. And we have to know how to get the timely data from global and the Indian source, international charter. As I said, so one has to know which are the source of data and how soon we can get data from them. So some kind of linkage has to be established. And we also should know how to do the value addition to the satellite data. Satellite data is just a picture. So a lot of value addition is required in terms of interpretation. So this value added product and the services has to be provided to people who need it on the ground. And disaster reporting through mobile apps, not only reporting, also the information can be disseminated through the mobile apps. And that is where some investment has to be made. So focus should be on disaster response. That is what if we do, the impact of disaster will be less and improve the quality of response. So this is also another area to be emphasized on. And the key issues which challenges remain a change in the policy paradigm to include remote sensing GIS in disaster management, which is still considered as only administrative issue in the country. In our country, the remote sensing GIS is, to the extent it should be implemented in real disaster management, a lot of scope is there for improvement. Techno-citizen centric approach is required. So in place of only management, approach, so technology and directly how to reach people and provide the information those who need. So that is very, very important. Prepare the special database before the disaster strikes. We should have the database, special database of the places which are often affected by disaster every year. Integrate indigenous knowledge while dealing with the disaster. A lot of, we have a 5,000-year-old civilization and we have grown in terms of knowledge, over last 4,000 or 5,000 years. So a lot of traditional knowledge is there how to deal with the disaster. So somehow in the present context, because of the infusion of technology and other things, we tend to forget those traditional wisdom and knowledge. So this has a lot of scope even today. So in combination with the modern technology, the indigenous knowledge, this should be incorporated to take full advantage of this modern technology. A regular drill, as a simple saying goes that in the present, the practice makes a man perfect. So regular drill using various possible scenarios of disaster will help to be in a position to deal with disaster when it really strikes. And another important thing is to anticipate disaster, make strategy for mitigation through spatial decision making. So you have to anticipate, we cannot anticipate that everything will go well. So for anything, whenever we make a dam or we are making a road construction or there is a big planning which is going on for the Kumbh Mela. So every time we have to anticipate disaster and accordingly make a plan with the help of special inputs. And the last but not the least important point is the mainstreaming. So consider disaster risk reduction as a part of developmental project. So when you do a developmental project, we do a construction of dam or road or bridge or anything, we make sure the impact of disaster is reduced. So that is the one point which our Honorable Prime Minister articulated in a 10-point agenda which he gave couple of years back at the ASEAN Ministerial Conference in Disaster Management. And he said that the mainstreaming is the most critical, and linking of the disaster risk reduction into developmental planning actually is the first point he highlighted should be given a lot of importance. So that is critical, that disaster, the development doesn't lead to disaster. What we have seen in our context at many places, that the developmental activities have been undertaken, but with the least regard towards the disasters. So that should be seen as an opportunity to improve the situation which was present even before, such that the impact of the development would be sustainable, and also it won't lead to another disaster. So the ultimate goal should be towards, once again I re-emphasize, it's a tall order claim, or it's a very wishful thinking, but it is achievable, and we must strive towards zero casualty and quick recovery, say within 24 hours. And business continuity plan is very, very critical to keep our economy activity and everything else, smoothly by quick recovery. So that's, moral of the story is that the Earth observation satellite data is very, very important for your own safety and the rescue mission if you are involved with. And we know that from hazard mapping to policy intervention, space technology can help. So we have to therefore use it to the great extent. So thank you very much for your for your listening to this lecture.